So Dr. Wright did her PhD in mathematics at the University of York in UK with Stefan Weigert, then went to the group of Anna Belen Science at ICTKT in Gdansk, Poland. Now she's a postdoc in the quantum information theory group of Antonio Assim at ICFO in Barcelona. She studies the foundations of quantum theory and applications to quantum technologies, in particular, quantum contextuality, Cauchy-Sprecher and generalized, non-locality, general probabilistic theories, and Gleason type theories. Let's all welcome her.
Hello. Thank you. Should I start whenever?
Yeah, please.
Yes, please go ahead.
Sure. Okay. So today, I'm going to present this work to you, which I did with Mate Farkas, who's also here at ICFO in Barcelona. And what we were doing is looking for a connection between non-locality and contextuality, by which I mean generalized contextuality. So non-locality and contextuality are two phenomena which we can see in quantum theory, which differentiate it from the classical physics that kind of came before quantum theory. So then a question that we can ask is, do they represent sort of two completely different and separate ways in which quantum theory is different from classical physics? Or is there some kind of underlying mechanism which connects both of them? So like, are they connected in some way? So in this work specifically, we were looking at non-locality in like a two-party scenario, so bipartite non-locality. And as I said, we're looking at generalized contextuality, but not every kind of generalized contextuality, just a subset of that. So those are the two things that we're going to connect. And the way we're going to do that is by looking at the correlations. So if you want to investigate non-locality, you would do that in what we call a Bell scenario. And then the phenomenon presents itself in the correlations that you can see during this special kind of experiment. And then what we do is we find a map that takes you to a correlation in a different kind of experiment, which we call a contextuality scenario, which shows you like the contextuality present in a theory. So I'll just go through what these two kind of experiments are briefly, so then we can see what the map actually does. So you're probably familiar with what Bell scenarios are. So we're going to look at the two-party case. So we have Alice and Bob, and they're doing these space-like separated experiments where Alice takes an input X, puts it into her device and gets an output A, and Bob takes an input Y, puts it into his device and gets an output B. And then we're interested in the correlations that we can see between these inputs and outputs. So by correlations, I mean, so if you have a theory that you think describes the setup that you have, it will tell you the probability of seeing A, B, given that they inputted X and Y. So for all the possible different values of A, B, X, and Y in your experiment. So then if you take the kind of list of all of these probabilities, this gives you a vector of real numbers, which you can then you can find the sets of these vectors that you can see in different theories. And we're going to be in this talk, I'll mostly concentrate on the quantum set of correlations, or specifically the quantum spatial correlations, because there are various sets of correlations that we can associate with quantum theory, but we're going to mostly look at the quantum spatial correlations. So this is a scenario where Alice and Bob share a quantum system, which we'll say is in some state rho. And then every time Alice inputs X, she measures some POVM MX and sees some outcome A. And when Bob measures Y, he measures a POVM NY on his part of the system. So then we can see that the probability of seeing A, B given XY is just given by the Born rule for Alice's measurement operator tensored with Bob's measurement operator on the state rho. So this is just what I'm writing here. So Alice's POVM is on some Hilbert space HA, Bob's is on some Hilbert space HB, and then the density operator is on the tensor product of those Hilbert spaces. And in general, we allow those Hilbert spaces to possibly be infinite dimensional. So this defines the quantum spatial correlations. So now some possibly distressing facts if you haven't seen them before. So this set of correlations isn't closed. So you can get like arbitrarily close to some point using quantum theory, but never actually realize that point. And this point will always be on the boundary, right? So some parts of the boundary aren't included in the set. In general, to realize any point in this set, you would need quantum systems which have infinite dimensions. So even if you have an unbounded finite dimension, like no matter how large that dimension is, there are some points that you will never be able to reach in this set. And possibly the most distressing fact is that the membership problem for this set is undecidable. So if I give you a general arbitrary correlation and ask you to decide, is it in the set CQS or not, there's no algorithm that you can apply that will always give you the correct answer. Yeah, unfortunate, but okay, so now we can move on to a contextuality scenario.
Sorry, is that a reference for this fact? So this is
yes.
undecidable?
Yeah, so if you look up Slofstra, Slofstra,
Okay. Is that IQC?
like, I actually don't know where he is,
okay.
But if you look up him with undecidable and quantum, you'll get like a few papers, and in one of those is this undecidability fact.
Okay, thank you.
Okay, thanks. Okay, so now our second kind of experiment that we're looking at is known as a contextuality scenario. And we're going to look at a special subset of those which investigate preparation contextuality, because there's also measurement contextuality and transformation contextuality, but we just care about preparation contextuality for now. So these experiments are pretty simple. There is an input X, which tells you how to prepare some physical system in some preparation PX. And then there's an input Y, which tells you a measurement to do on that system that you've prepared, and then you see some outcome B. So you can describe the behavior of the experiment by, so I'll call these Q, but just for the probability of B, given that you prepared X and measured Y. So this is just known as a prepare and measure experiment, and on its own, it doesn't tell us very much. But so we need to introduce another concept, which is important to contextuality, which is called operational equivalence. So if I have a preparation P and a preparation Q, I say that they're operationally equivalent, which I denote like this. If there is no measurement that can tell them apart in the theory, even statistically. So if I was to give you a black box and tell you that I'd prepared a system inside it using the preparation method P or the preparation method Q, there was no measurement that you could do on that system which would be able to tell you which one, even if I give you a large number of the boxes. So even statistically, you can't tell them apart. So this is just represented by this equation that I've written here, which is saying that for any measurement M and outcome A, the probability of seeing A, given that you measure M and the system is prepared with P, is always equal to the probability of seeing A, given that you measured M and prepared the system in Q, like for any measurement. So all the statistics are the same. So then we want to involve this concept in our prepare and measure experiment. So the way that we do that is, so we have these various preparations that we make, and then we impose that there has to hold some operational equivalence between some mixtures of them. So for example, I could do an equal mixture of the preparations 1 and 2. So like I flip a coin and either do preparation procedure 1 or 2. And then I say that that gives me something which is operationally equivalent to doing an equal mixture of P3 and P4. So the prepare and measure experiment together with this equivalence is a contextuality scenario. And again, for this talk, I'm going to be interested in the set of these correlations, which we can see using quantum theory in one of these experiments. And I'll call this set Q. So in this case, every time I do an input X, then I'll have some density operator, rho X, which describes my preparation. And for every measurement Y, I'll have some POVM, which I'll call NY, representing that measurement. And then operational equivalences in quantum theory literally just mean that the density operators are equal to each other. So that would mean that if I take this a half and half convex combination of the density operators for the first preparation and then the second one, they're just mathematically equal to this 50-50 combo of P3, row 3 and row 4. So those would be the conditions for quantum theory. And then the theory would tell me that the probability of seeing B, given that I inputted X and Y, was given by the Born rule. So it's the B outcome of my POVM times the density operator rho X. So maybe you haven't seen a contextuality scenario before. So just a quick example. So here are some states that would satisfy this operational equivalence, which I gave you as an example. So if this is a plane of the block sphere, I can take rho 1 to be an eigenvector of the Pauli Z operator, and rho 2 to be the other eigenstate of the Pauli Z operator. And then if I do a 50-50 mixture of these, you can see that the point is like the center of the block sphere, which is the identity over 2. And then if I take rho 3 and rho 4 to be the eigenstates of the Pauli X operator, the plus and minus states, then also a 50-50 mixture of these is the identity over 2. So then they satisfy this relationship, right? So if this was my contextuality scenario, these would be some like valid preparations that I could make in quantum theory in this scenario. So then you've chosen what the preparations will be, and you can also choose what these POVMs NY should be. So for example, I can choose the ones that are represented on the block sphere like this. So like N0 is kind of diagonally in between these in this direction, my states, and N1 is the sort of diagonal that's halfway in between in the other direction. And if I choose my measurements like this, I end up with a correlation which is on the boundary of the quantum set, and it's somehow as far, and it's outside this this polytope in the middle, which is called the non-contextual set, which I haven't actually explained to you yet. But you can just think of this as the correlations that you can see from classical physics in a contextuality scenario. So here we've ended up with a point which is outside the classical set. So, and it's somehow like a maximal violation of a contextuality inequality, which is kind of the analog of a Bell inequality, if you know what those are. So if you want later, I can kind of explain the meaning of a non-contextual theory, but for now, you don't really need to know for this talk, so you can just think of it as the set of classical correlations. Okay, so maybe that was a bit much if you haven't seen contextuality scenarios before, so I just really need you to remember 3 things. So in these scenarios, you have preparations, and then once you prepare your system in that way, you do some measurement on it. That's the second thing. And then the preparations have to satisfy some equivalences, which means that a convex combination of the density operators is equal to another convex combination of the density operators. So there are just kind of 3 ingredients to a contextuality scenario, a preparation one anyway. So now we can ask the question, how do we relate this to non-locality? So here we seem to have just one system that we're doing our experiment on, but in non-locality we had 2. So how are we going to connect the 2? And the answer is by the idea of remote state preparation. So this means that I'm going to view my Bell scenario as, for example, Alice does a measurement, and that prepares for Bob a system, like remotely prepares his system in a certain state. And then he does a measurement on that system. So if you just look at Bob's side of the experiment, it looks like a prepare and measure experiment where the preparation is done by Alice remotely for him. So if you imagine our Bell scenario, and then we are in some frame of reference where it looks like Alice does her measurement first. So she chooses an X, inputs it, does her POVM MX, and sees an outcome A. And then depending on what her choice of A was and what her choice of X was and which A she saw, Bob's system can now be in some different state. And so we'll call that state rho of A given X. Quantum theory tells you what that state will be, right? So you just, you take rho, which was the state of the joint system, act on Alice's part with her measurement operator, and then trace out Alice's system to see the state of Bob's system and normalize. So this describes the state which Bob is left with, and then going back to imagining what happens next in our Bell scenario, Bob chooses his input Y, does his POVM NY, and sees some outcome B. So he has some preparations and does some measurements on it. So this is how we're getting the prepare and measure idea. And then the final thing that we have to notice is that there is a relationship between these rho A given X's, which comes from the fact that quantum theory satisfies the no signaling principle, which means that the average state that Bob receives, so if we sum over the probability that Bob receives rho A given X, which is given by this value here, Alice's marginal probability of observing A given that she inputted X. If we sum over these multiplied by the state rho A given X, that gives us the average state that Bob receives when Alice inputs X. And what we know is that so that Alice can't send a signal to Bob, this needs to be the same state as if she inputted any other X prime. Because if these two states are different, then there is some measurement that Bob can do which will statistically differentiate the two, which means that Alice could send a signal to Bob which arrives faster than the speed of light. So now what we've got here is a convex combination of our density operators is equal to some other convex combination of our density operators by the no signaling principle. So if I just look at kind of my experiment through in this way, we can see that we have the three ingredients that we needed for a contextuality scenario. So we have some preparations, and then we do some measurements on them, and those preparations satisfy some equivalences given by this equality here. So then what we see is this is a contextuality scenario. So as an example, imagine you're in your CHSH Bell scenario and you're trying to maximally violate the CHSH inequality. So you prepare your system in the maximally entangled state, and then Alice does a Pauli Z measurement and a Pauli X measurement, and Bob does these diagonal measurements, which are the same as the ones I was explaining before. So this would maximally violate the CHSH inequality. But now if we think about it in our remote state preparation way, so we think that Alice goes first, and if she sees the 0 outcome from her Pauli Z measurement, this leaves Bob's system in the state 0, and this happens with probability 1/2. So this is his rho 0, 0. And the other outcome for Alice also happens with probability 1/2, so rho 0, 1. So that then we end up with these two states with 50% probability, and so they mix to the identity over 2. And then we get the same thing for the Pauli X measurement of Alice. You end up again with this plus and minus states, which mix to the identity over 2. So then we kind of have the same example that we were looking at earlier for the contextuality scenario. So in this way, you can kind of see that when we were in the Bell scenario and we maximally violated a Bell inequality, this has mapped to a contextuality scenario where we maximally violate some contextuality inequality. So now we have this kind of intuition for how to go from our Bell scenario to our contextuality scenario. We can describe the map between the correlations. So if we were in the Bell scenario and our correlations were described by this P of A, B given X, Y, then if we view it as a contextuality scenario, then we see that the probability that Bob gets outcome B, given that Alice prepared for him this row A given X, which I'll just denote like this, and he did measurement Y, is just equal to P of A, B given X, Y, but then we've assumed already that Alice got the outcome A, so then we just have to divide by the probability of her getting the outcome A. So this is the map. It's quite simple. And you also have to say which Bell scenario you're mapping from and which contextuality scenario you're mapping to. So the Bell scenario is just described by the number of outputs for Alice, outputs for Bob, inputs for Alice, inputs for Bob. So this AB given XY, AB, XY, these four numbers describe the Bell scenario. And then this tuple here describes the contextuality scenario that we're going to map into. So this first number is the number of preparations. So we want to have all of the pairs AX that we had in the Bell scenario. So then we just multiply A and X together. And then Bob still has Y different measurements. So this is the same Y here. And he still has B different outcomes. So this is the same B here. And then the final two parts of this tuple are the preparation equivalences and the measurement equivalences. But there were no measurement equivalences, and that's not something I explained to you. So we just put the empty set here. And the preparation equivalences are just given by the no signaling condition, which I showed you. So saying that the average preparation when Alice inputs X is equivalent to the average preparation when Alice inputs any other X prime. So this gives us some preparation equivalences. So it tells us which scenario we're going into. So there are two things to note here. The first thing to note is that, so this tuple is describing the contextuality scenario that we're going into, so the experiment, and it depends on PA. So PA is the marginal of this correlation. So if you're in one Bell scenario, you can map to multiple different contextuality scenarios, which are kind of indexed by this PA here. So every time you have a different marginal for Alice, you map into a contextuality scenario, which for these numbers are the same, but the coefficients here in this equivalence vary over all the different possible options. And the second thing to notice is that here we have an expression where we can be dividing by 0, which is not good. But if you think about it, if PA of A given X is 0, that's saying that the probability Alice observes A given that she inputted X is 0. So that outcome never occurs in the Bell scenario, which means that this state row A given X is never prepared. So in the actual paper, what we do is that we map to a scenario where that preparation isn't present. So that's just going to mean that this number of preparations actually also depends on the correlation, because if you have a correlation where an outcome A doesn't occur for Alice, then that means that the number of preparations is kind of reduced by 1. So this number here will actually also depend on P, but for simplicity, kind of in the talk, I haven't included this. So this is going to be our map, which we will call lambda. And yeah, this depends on P. So just a quick note that, so we're mapping from two-party Bell scenarios into contextuality scenarios, but not all contextuality scenarios. So they must include only preparation equivalences. So these are kind of the things that I've been describing to you. There also exist some things which are called measurement equivalences. So if our scenario includes some of those, then that's not something we'll map to. And the preparation equivalences have to have a certain form. So they have to be multiple decompositions of some given preparation. So they basically just have to be this like string of equivalences that look like this. If I have two separate equivalences, that's like a valid contextuality scenario, but it's not one of the ones that we can map to from a Bell scenario. And similarly, within these equivalences, every preparation has to appear only once. So if I have something like this, so this is one string, so it looks good, but then this P1 appears everywhere, and so this P3 appears twice well, and there's no way that you can rewrite this in this form. This is something that we show in the paper. So this is also not a scenario that we can map to. So this was a map. So we're here on the left-hand side, we have a Bell scenario, and then we have some correlation in the quantum set. And basically the argument that I just showed you with the remote state preparation shows you a way to deduce that you map to a correlation which is also in the quantum set. So it gives you a quantum realization for this point here, Q. And you can use some kind of simpler arguments to show that if you started in the local set, you end up in the non-contextual set. So like the classical correlations map to the classical correlations. This was quantum max to quantum. And then there's also the non-signaling set. So this is a more general set of correlations than the quantum one. This maps to the kind of the largest set of correlations in the contextuality scenario as well, which we just call C for contextual. So like if you allow a generic contextual theory, then you will be able to access all of these correlations. So this is kind of good. This is what we kind of would want as a property of our map. It like preserves the different sets of correlations that we can see in our different theories. But at the minute, we've just thought about one direction. What about the other direction? So can I access every different quantum correlation within these scenarios from some quantum correlation in a Bell scenario? So essentially this question is, so now we're in our contextuality scenario. We have some quantum states for every one of these preparations. We're still going to label them as AX, like for convenience. And these states satisfy this equivalence. And we want to ask whether there is a way that Alice can remotely prepare these states for Bob generically. So if I have any rows which satisfy this, is there a way that Alice can have that Alice and Bob can share a joint state and Alice does some measurement and Bob is left with these things? So the question is, yeah, this preparation part of the experiment, can I think of this as Alice performing a measurement on some half of a quantum system? So if this is all happening on some Hilbert space HB, then we're looking for some Hilbert space HA, which we can tensor with HB. And then we're looking for a state rho on this joint Hilbert space and some measurement operators for Alice MXA, such that if I apply those to Alice's half of rho and then trace out her system, I am left with the states that we want to have. And the answer is yes, hooray. And we know this because of what's called the Schrödinger HDW theorem. So if you've heard of quantum steering, the question I'm asking you is basically just a steering problem. Can you steer a state into any possible assemblage? So this kind of thing is called an assemblage. And this theorem tells you, yes, it's possible to steer into any assemblage in quantum theory. So at the bottom, I've just written down the construction, which allows you to do this in finite dimensions. And we also kind of showed that it works for infinite dimensions in the paper, like the construction's slightly more complicated, but it works with the same idea. I won't go through this exactly, but basically the answer is yes, you can find these measurements mx, which will steer your system into any of these row axes which satisfy this condition. So now we basically have our map, right? And what I've just told you means that if you're in the quantum set here and you take the inverse of this map, you also end up in the quantum set here. So in some sense, you have an isomorphism between the quantum correlations in the Bell scenario and all of the quantum correlations in all of these contextuality scenarios on the right-hand side. And similarly, you can go from non-contextual to local and from contextual to no signaling. This works. So this was our map. So now some consequences that we can find now that we've constructed our map. So I told you at the beginning that the membership problem of this quantum set of correlations in the Bell scenario was undecidable. So now from our map, it follows that the membership problem of the quantum correlations in contextuality scenarios is also an undecidable problem. I also told you that CQS was not closed. So this implies that Q is also not closed. And similarly, CQS, you require systems with infinite dimensions to realize every quantum correlation in this set. So you also require infinite dimensional systems to realize every correlation in the set of contextual correlations. And then finally, there's one that I didn't introduce earlier, but there is this result, which is known as MIP star equals RE, which doesn't tell you a lot if you haven't heard of it, but a result, this tells us something about non-local correlations in Bell scenarios, quantum correlations. And the consequence of this is that there is no algorithm that can verify that a behavior or a correlation in a contextuality scenario is epsilon far away from the quantum set for all epsilon greater than 0. So that's a bit hard to process. So, and we're using the L1 distance. Yeah, but that's a bit hard to process. So I will kind of describe what that means. So we found out that we have our quantum set Q and that it's not closed. So we can consider here Q bar, the closure of this set Q. And then we can consider some point which is outside of the closure. So then what the final point on the last slide was saying is that there is no algorithm such that if it's given a point which is outside the closure, it can verify for you that that point is outside the closure. And if it's given a point that's inside the closure, either it tells you that it's inside or it just doesn't halt and it goes on forever. But this would basically verify for you, given any point that's outside, it can verify that it's outside. And our map implies that there is no such algorithm that does that. So a kind of consequence or a specific example is that there are these hierarchies of SDPs in the literature which approximate this set Q. And our result shows that these hierarchies actually don't converge to Q or to the closure of Q. So what these hierarchies do is, so there is an NSDP which decides, so semi-definite program, which decides whether a correlation is in some set Q1, which is a superset of Q. And similarly, there is an SDP which decides whether your correlation is in a set Q2, so this is a subset of Q1, and then there are different levels of this hierarchy, and it continues on kind of for any natural number, and the sets get smaller and smaller. So then you can eventually consider like the intersection of all of these sets, which we know will be some outer approximation, so some superset of the original set Q. But now what we know from our result is that you don't actually converge to the set Q or to the closure of Q. So there is some, sorry, I'm gonna sneeze. Sorry, there is a gap between these two sets. So maybe I'll just talk a bit about how we know this. So the result that I was telling you about, MIP star equals RE, one consequence of that is that the weak membership problem for the set CQA, so CQA is the closure of CQS. So I was telling you before that the quantum spatial correlations, this set isn't closed, so you can consider the closure of it. So the weak measurement problem for this closure is undecidable. And the weak measurement problem means you choose some epsilon greater than 0. And then you're promised that the correlation that you're given sorry, is either epsilon far away from this closure. So if this is kind of an epsilon ball around the closure, then our correlation is outside of this ball, and it will tell you that it's outside this ball. Or the correlation that you're given is actually inside the closure, and then the algorithm would tell you that it's inside the closure. So basically, you're just promised that it's not in this area that's between, that's within, which is epsilon far away, but not inside this closure. So this is deciding this problem is the weak membership problem, and they show that this is undecidable. So there's no algorithm that does this. So then, how does our result show that these hierarchies don't converge to the quantum set? So if they did, so if Q infinity was equal to the closure of Q, then the algorithm I'm going to describe to you now would be able to decide the weak membership problem for CQA. So you take your correlation, which you're promised is kind of outside this epsilon ball or inside CQA, and then you use our map to map it into a contextuality scenario, into a correlation in a contextuality scenario, which we'll call Q. And then you kind of iterate over these two steps. And the first kind of thing that you do is you run level D of the hierarchy, and if you find that your Q is outside the set defined on level D of the hierarchy, then you know that P must be outside of the epsilon ball, because you know that Q is outside of the closure of Q, and it's also, you're kind of promised on the non-locality side that it's not going to be epsilon close, so then you know that P is outside of the epsilon ball around around CQA. But then if this is not true, you go on to the other step, which is kind of approximating from the inside. And for this step, so you fix some delta, which is less than epsilon, and then you create a net of correlations that can be realized in quantum theory in dimension D. So this is going to look something like this. So maybe these are the correlations that I can realize with 2 qubits in a spatial sense. So I create like a net of these points such that every point that I could realize with qubits is at least delta close to any one of the points in my net. So you can do this by just kind of parametrizing the space of measurements and states of 2 qubits. And then if the correlation P that you were given is delta close to any one of these points that you created in your net, then you know that it must be inside of CQA, because you were promised that the point was either inside CQA or epsilon far away from CQA, and our delta is less than epsilon. So then so you do this for dimension D, and then if you find out that's not true, you continue on to like the next level of the hierarchy, and then you go to the higher dimension and you keep going, and then eventually it's gonna the program will halt one of either ways, is the idea. So then you can decide the weak membership problem, which we know is undecidable. So then, yeah, we found that this Q infinity is not equal to the closure of Q. Okay, so I'll just finish with some kind of open questions that we that have arisen due to what we did. So this set Q infinity, which is the limit of the hierarchy of STPs, like what is it? Because it's some superset of Q, but we don't have some kind of physical or even mathematical characterization of it. And then what does it map to in kind of the Bell scenario setting? So we can kind of map backwards using our map. And we know that it's going to give you a superset of the quantum spatial correlations, but what superset will it be? So one candidate for what it could be is the set of quantum commuting correlations. So these are the quantum correlations that you can get where instead of, so our quantum spatial correlations were given with the tensor product formalism, but now instead we just consider like states and measurements on one big Hilbert space, but then we require that Alice's and Bob's measurements commute. So like this, so if you took the one big Hilbert space to be the tensor product one, then obviously Alice's and Bob's measurements would commute because they're just like some M tensor the identity and some identity tensor M. But more generally, you could consider this, and another consequence of this MIP star equals RE result was that these two sets are not equal. So the closure of CQA was not equal to CQC, the quantum commuting correlations. So yeah, one possibility is that this set is what our Q infinity would map to. And there is a hierarchy of STPs which converges to QC. So this is the NPA hierarchy, which you may have heard of. So then this would kind of make sense in that we have some STPs which convert on the contextuality side to the kind of the image of this set. So that would make sense. So it's possible that this maps to CQC, but if it doesn't, we have, I guess, defined some new outer approximation of CQS, which would be also interesting. And then also, if it doesn't, then what is the image of CQC in our contextuality scenario? This would be some other kind of interesting set to investigate. And then another thing that we would like to do is to now that we have this map, we can transfer kind of many results that are from non-locality to contextuality. So if you've heard of self-testing, this is something we're interested in doing. So there are like points in the non-local set where if you observe that point, you can kind of certify the quantum states and measurements that were being used. So then this is something you could also do with the contextuality experiment. So then this is something that we're going to look into now. And then also the case for multipartite Bell scenarios where you have more than two parties. So our result doesn't kind of easily and obviously generalize to this because of some property that's known as post-quantum steering, which basically means that this theorem that we used, this Schrodinger HJW theorem, kind of doesn't hold anymore once you go to multi-parties. So then our kind of mapping breaks down. So we would need to think of some other way to map multipartite Bell scenarios into contextuality scenarios, and maybe it's not possible, or maybe it is possible. So that's something we would like to find out. Okay, so here is my meme to encourage you to study contextuality, and thank you for listening.
Hey, thank you very much for your talk. It was a great talk and funny. This last one got me. So now I'll open to questions. Does the audience have any questions for her? Oh, I think we have one.
Hi, can you hear me?
Yes.
Yes.
So I do have some questions here. So one of the questions is, I guess, some confusion that I've got from your talk. So I think you were saying that there's some constraints, maybe, if I understand correctly, about this mapping, because maybe not all contextuality scenarios could be mapped to a Bell scenario. So what does that mean? Because you also say that there's this inverse map that you could define. So do you mean that you could have this kind of isomorphism only for certain scenarios?
Yeah, exactly. So the scenarios which are on this right-hand side are a specific subset of all contextuality scenarios. So if you restrict to that subset, then you get the isomorphism. But if on this side you wanted to have sort of the generic contextuality scenarios that are kind of from the literature, your map would only take you to the subset that we've described kind of in this talk, right? So if you look at this subset of scenarios, you get an isomorphism, and the map doesn't take you to. So the map kind of takes the correlation and the Bell scenario, this pair of things, to a correlation and a contextuality scenario, this other pair of things, and this scenario will always be of this specific type.
So I guess, so correct me if I'm wrong about this. So if I start with any contextuality scenarios, then I could always do this inverse mapping. But if I start from, let's say, a given Bell scenario, it may not, through this mapping, gets mapped to a meaningful contextuality scenarios. This is how I should understand this.
So I think maybe not. Maybe the idea is, so the map only, so if you start on the contextuality side, the map only makes sense, is only defined for scenarios of this specific type. Like the map kind of doesn't, so you won't be able to write your correlation like this if it's from some scenario which has like different measurement equivalences. So like you won't be able to label your preparations with these pairs of numbers in a way that fits with the, wait, where is this thing? Is it here? No. Ooh. Which fits with this kind of labeling. If you're in some contextuality scenario where the equivalences don't look like this. So yes, so if you're doing the inverse map, then you have to start in one of these contextuality scenarios in order for the map to be defined, and then you'll end up in a Bell scenario. And then if you start in the Bell scenario, you will end up in one of these contextuality scenarios.
So I guess the reason why I'm asking this is because I think for some of this, let's say, features that you mentioned earlier, let's say also about the one essentially translating the results from Bell scenario for MIP to REs, MIP cycles, RE, and so on. So some of these results, they are for specific Bell scenario. For example, when you say that the quantum set is not closed, this is, I mean, in general, it's not closed, but there are certain Bell scenarios where this is closed.
Yeah,
so
exactly.
This translation and so on.
Yeah, so I guess when I say it's not closed, I mean in general it's not closed. So then also on the other side, in general, Q is not closed, which kind of trivially kind of applies to every single contextuality scenario because it's true for this subset of them. Yeah, so you're exactly right. Like these results are just kind of for a subset, but because they're results kind of about the general case, then it's true, right? You know.
Yeah. So but because there's also some restrictions about this scenarios as we were just discussing. So I'm wondering whether you could indeed import all these results from Bell scenarios directly to.
Yes. So I think like for example, maybe what you're saying is that so when you have a case where CQS is closed, like in the 222 case, the scenarios, all of the scenarios that you map to will then also have closed quantum sets. So this will also apply. Yeah, it's a good point. Like there are many other results that we can map across now.
But about also this undecidability problem, would it also get mapped to a meaningful non-contextuality scenario? Is it obvious?
So you mean this here?
No, the last one, the MIP star equals RE. Because I guess, okay, I'm not familiar, or I don't remember so much about the proof of Slopstra. I mean, there are also other proofs available out there. But they were for specific. Maybe they have some, I don't know, some explicit proof for certain Bell scenarios. How would that constrain when you try to apply this map and apply the results to your non-contextuality scenario? I was just worried that there's some kind of some kind of overlooking of consistency here. But maybe you have got all this sorted out.
Yeah, so I mean, the idea is that because there is at least one Bell scenario where the membership is undecidable, then that implies there is at least one contextuality scenario where the membership is undecidable. So then the statement that in general the problem is undecidable holds, right? Because I could give you the a correlation from this scenario where it's undecidable, right? This is the idea.
Okay. So another question. Okay, maybe I should not be dominating this whole thing. I should leave. If nobody asks more questions, I will continue.
I think that, I don't know, nobody raised their hands. So if anyone wants to ask a question, please raise their hand. If not, I think you can continue.
Okay. So I'll just ask more.
Okay.
So this construction was done for the considerations of this preparation non-contextuality. So could you also get something done for measurement non-contextuality?
So this is something that we haven't managed to do so far, but we're trying to think of if there are ways to do it. So the kind of contextuality we were looking at here is from this like Speckens construction, the generalized contextuality. So if you look at the other kind of contextuality, like the Cauchy-Specker kind, there you have this assumption of kind of determinism of the underlying model. So maybe not super important, but the idea is there is a mapping between non-locality and contextuality. But this mapping kind of breaks down when you go to the generalized contextuality case, because we no longer kind of assume this determinism of the kind of underlying ontological model. Kind of we end up with some problem there. So far we haven't thought of a way to. So what you would need to do is show that some measurement equivalences hold. Like if you look at your Bell scenario in some certain way, then there are some equivalences between the measurements which hold. And we haven't managed to think of a way that would be true yet. But it is kind of interesting that this works in this Cauchy-Specker case, this different kind of contextuality. But we haven't found a way to integrate that into the generalized contextuality picture here.
Okay. So maybe one last question. So this semi-definite programs that you talk about in this non-contextuality scenario. So from your explanation, it seems like it has nothing to do with the MPA hierarchy. It's not like I could think about it as a mapping from the MPA hierarchy, maybe through the mapping that you have established. So it's not something I can understand in this manner.
So it's not defined like that. It's like defined within the contextuality picture, but it is constructed in a very similar way. So if you know the MPA hierarchy, you make these moment matrices and you see if you can find a moment matrix. So you do a very similar thing in the contextuality scenario. You end up having to find kind of multiple moment matrices, but it's like the same kind of procedure. And then something we would like to know is whether these sets map to each other, right? So it's not known at the minute, but it could be that some level of the MPA hierarchy is, maps to some level of this hierarchy. I think it's probably unlikely that it would be like exactly the same level, but like there probably could be some mapping. And in particular, this final one of these open questions I was saying is, do they converge to the same thing? So that would be maybe the most interesting question. And we think this is probably going to be true, and this is what we're kind of going to work on now. And the kind of nice thing about this question is that in the NPA case, you have this physical interpretation of what the hierarchy converges to, right? Because it converges to the set of quantum commuting correlations. So then that's what we're going to try and use to so we kind of apply our map to these commuting correlations to see what you get on this side. And then if we know that the everything within the hierarchy would satisfy those constraints, then you'll be able to see that you're mapping to this set Q infinity. But it's a good question. Yeah.
Okay. All right. Thanks very much.
Oh, thank you. They were good questions.
Well, we're almost at the top of the hour here. Oh, but we do have one more.
Before shooting this question, because I have another meeting at 5, so I would like to first thank you for giving such a nice talk.
Yeah,
and
thanks for the
hope
invite.
to see you, hope to see you soon.
Yes.
Okay, thank you so much. Okay.
Thank you too.
I will bye for now. Bye.
Bye.
Okay, I think Gelo has a question, right?
Yes. Can you hear me?
Yes. Hello.
Yeah. Hello. Just a naive question. So in the mapping, so if I go from the contextuality scenario back to find the Bell scenario, so like so in your tuple, so the first number is sort of like AX, right? So I was just wondering, so let's say like AX is 16. So I could divide that, it's like 4 times 4 or 8 times 2. But I suppose like some of the extra details will tell me which one is the correct scenario, right?
Yeah, exactly. So when you write down this, so you also in the tuple, you have these equivalences, which are here. So then the number of preparations you kind of have so this will be like multiple things which are equal to each other, right? And the number of preparations you have in each one of these inequalities will be kind of tell you the number of outcomes for Alice for each one of her measurements, right?
Okay, so then this should be uniquely determined.
Yes, but it's actually was a bit particular in the end. So if you kind of look in this picture, you will see that my tuple looks a lot more complicated than it does in the one that I presented to you. So in order to make this work, you have to kind of be very precise. Mostly because
I was even wondering, like, so if the first number was like some prime number, like 13, but I mean, of course, it just means that maybe there's some A that you don't see, therefore that reduces the possibilities by 1 from some so
exactly exactly. This is good thinking though. Like this took us like a while to actually sort out in some way where you get something invertible, but in the end so what actually happens is, so you take this pair of the correlation and the scenario, and then you map it to this pair of the correlation, the scenario, and then you also have to put an extra term which kind of reminds you where you took out any whether it were any zeros in the original correlation. So you kind of have to take a note of where the zeros were. But I didn't really explain this because I think maybe it's not super like meaningful, in that like another way you can think about it is if you're in the Bell scenario and there is some outcome that never occurs, it's kind of like you're in a kind of lower Bell scenario, right? It's like a Bell scenario with a lower number A here. So then that scenario would then, if you look at all the kind of correlations that don't have zero marginals in that scenario, then you map in a kind of easy way. So you can kind of think of it as, you end up going down this list of Bell scenarios.
I see.
Instead, if that makes sense. But that was good thinking, and we had to we had to figure that out.
Okay, so thank you. Yeah, that's
Thanks.
All right. Perhaps I'll wait a little bit to see. Yes.
Hi.
Christian?
I just wonder, is there a simple state, like simple example thing I can see is lying in the non-contextuality, the square of non-contextuality, because like I know the partial trace of the entanglement, maximally entangled state is identity, so it's right in the quantum sphere. Then I just wonder, is there any like a state like that, and I can know of it rise in the non-contextuality part.
So you want some way of thinking about the non-contextual set, like how to define the non-contextual set? Is that
Yes.
And you want so you wanted it as like an analogy from something in the local set. What was your analogy? Sorry.
So I mean, like in here, like the equation is like just like the maximally mixed state, right? Like,
so you mean if you restrict like your quantum correlations to the maximally mixed state, you end up with the local set? Is that what you're saying?
No, I mean like in like so from the example you give here, so I got some impression like so one in the border of this content in the content in the contextuality scenario is like a maximally mixed state. And I just wonder then what is inside this the classical regime in the contextuality scenario.
Thank you. Sorry, there's some like sound in your background, so I'm not super sure. But maybe so the sorry. There's so if you're thinking of what the analogy is in general for this identity over two, this maximally mixed state, this would always be if you trace out Alice's system, you're always that's the thing that you're always going to mix to. Do I have this example here? Maybe I don't. But yeah, so the thing that you will always mix to in the contextuality scenario, that all of these things will always be equal to if you take the row and then you trace out Alice's system. These will always be equal to that density operator.
Okay. Or is there an easy way I can see like what will rise in the non-contextuality square there? Or
so yeah, so then these, they're not defined with the Born rule, right? These are defined using what we call a non-contextual ontological model. So this sounds like a lot of words, but kind of the basic idea is, so you imagine that your system is always in some like hidden state lambda, and every time you make a preparation, that is just some kind of measure over these states. So basically, just with some probability, you're in one of the hidden states, and with some other probability, you're in another one of the hidden states. And then the assumption of non-contextuality is that if the two preparations look the same, so if you have this P being operationally equivalent to Q, then these two kind of probability distributions over your hidden states have to be the same. And then So this is kind of the non-contextual part. And then the ontological part is that you get the probability. You get the probability of seeing some outcome, given that you prepared P and measured M, is going to be equal to. So you kind of integrate over all of your hidden states, and then you take this kind of measure which corresponds to your preparation P, and then you also take, so you have like the probability of seeing an outcome A, given that you measured M. Oops. So this ontic state here, this hidden state, gives you the probability of seeing any outcome of any measurement, and then you just have to kind of integrate over the probability that you're actually in that hidden state. So if you combine all of these things together, then everything that you can get is in this non-contextual set. It's kind of a lot to take in at the beginning, but the non-contextual part is saying that if two things look the same to you, like if they're operationally equivalent, then they are fundamentally actually the same thing. So they're the same probability measure over these, like what the actual state of the system is.
Does it imply like, so there's like the equation like in the middle, like the one half of rho 1 plus rho 2 equal to rho 3 plus rho 4?
Yes.
Then
So
the rho 1 and rho 2 are exactly the same as rho 3 and rho 4. I mean, respectively.
So yeah, it would be the kind of equal mixture. So we always say that you can, in a kind of general operational theory, you can always like mix two preparation procedures. So it's like half the time I do one and half the time I do the other one. Then those two mixtures are equal to each other, but not necessarily the kind of it's not like rho 1 is equal to rho 3 and rho 2 is equal to rho 4.
Okay.
Like in the quantum case where you have like, so like rho 1 and rho 2 and rho 3 and rho 4 can be these four different states, but then they mix to the same thing. So then you can have these different preparation procedures, but they just have to mix to the same.
Okay.
I think perhaps we were not hearing you, Sasha, but I think you finished this question. There are any more questions? Okay, so I guess that's it. Let me thank you again for your very nice talk and agreeing
for the invite.
Yeah, for sure. It was very interesting. And oh, let me stop the recording.
Oh yeah.